All right, hey everybody, welcome back. In the next series of videos, we are going to examine something completely different. So complete turn away from sequences and series. We are going to round out our semester by looking at a couple different tools or new subjects that will be valuable to us in Calculus 3 and or are valuable in many applications, things like computer science, physics, robotics, and so on. Over the next series of videos, the next few videos, we will be introducing one of these subjects, which is the subject of parametric curves. In this video, our goal is simply to introduce what a parametric curve is. Okay, and so here is the formal definition. A parametric curve, and for us this will be a parametric curve in the xy plane, is a curve that is defined using a parameter. Oftentimes we'll use t as our parameter, such that each input point in the parameter t corresponds to a single point x comma y on the curve, right? And so because every single t will correspond to a single point, x and y on the curve, I can think of the x coordinate as being influenced by the parameter t, and also the y coordinate as being influenced by the parameter t. So I'll often write this as a set of two equations, x of t and y of t. And so if this is our parametric curve, I will often call these two, the x of t and the y of t, I will call these my parametric equations. Okay, and it is a fact that we'll demonstrate here that every sort of standard curve that we think about or talk about or can draw can be written as a parametric curve, and that includes curves that are typically functions as well as those that are not functions. So let's see just sort of a silly example of this. If I wanted to draw a function, right? So let's draw the function y equals, so let's draw the function y equals sine of x. Starting at, let's say, between 0 and 4 pi. Right, so the sine function starts here, that's 0 to 2 pi, and then once more, it will be 0 to 4 pi, and it will end there at x equals 4 pi. Great, so notice the way that I drew this, right? I had a single, point on my pen that started here and then just traced out the curve itself. And this is a great way to think about parametric curves, right? A parametric curve, I think of it using a parameter, often t. I can think of that t parameter as representing time. And as time flows forward, I can think of my parametric curve as being traced out in time. So maybe at time t equals 0, I'm right here. And as I flow forward in time, at any given point t, I'm pointing to a specific point here on the curve, and that would be a point x comma y. That would be the x coordinate at time t and the y coordinate at time t. If I float a little bit further forward in time, maybe now I'm right here, this would be again described by an x and a y coordinate at a single point in time. So a specific x of t and y of t, and so on and so on. So what I can often do is explicitly identify what my x of t and my y of t are, and that will help me describe, well, that will give me the parametric equations, and that will help me describe this parametric curve. And there's a really slick way that we can do this for functions, right? So functions that can be written in the form y equals f of x. Here it was y equals sine of x, but more generally, we can think about functions of y equals f of x. And for those curves, I can parameterize that curve by constructing a function x of t comma y of t as follows. I can describe this using a x of t comma y of t as follows. I can let my x of t just be the function t, right? So just x of t equals t. And then I can let y of t be equal to whatever my original function was. So f of t, or in this case, that would just equal sine of t. Right, so we can graph each of these parametric equations on their own set of axes if we wanted. And doing so, maybe I'll do this sort of lower down here, right? So this can be, I'll draw two sets of axes. Right, the first one is graphing t and x of t. And since x of t just equals t, that's going to be this function right here. My second one will be t and y of t. And since y of t, in this case, was just sine of t, that will look like this. Right? But then when I combine these two and to describe the point x of t comma y of t, we see what happens back in this original picture. Right, so at time t equals 0, I have my x of t is equal to 0, my y of t is equal to sine of 0, and so I'm right here at this point. As I flow forward in time, my x-coordinate will march steadily forward, right, because x of t is just equal to t, so as I go forward in time, my x values will increase steadily, while my y values will follow the expression sine of t, which means that they'll start at 0, my y values will go up to the number 1, they'll drop back down to the number -1, they'll go up to 1 again, they'll drop back down to -1, right? They'll keep oscillating the way that the sine function does. So again, my x values will just go straight forward in time. My y values will oscillate between +1 and -1. And when I consider the point x of t comma y of t, right, my x's are going forward, my y's are going up and down, and taken together, they will perfectly trace out this curve. So this is a nice strategy for turning any function y equals f of x into a parametrized curve, x of t equals t, y of t equals f of t. What's valuable though, or a valuable thing to point out is, as it says down here, we can write curves as a parametric curve, even those that aren't typically described as functions, right? So here is another example, sort of complete new example on the right side of the page here. Let's take a look at a curve. And I'll graph this in space, right? So let's take a look at a curve. And I don't have a formula for it, but it's going to be a figure 8. It's going to start here, and then it's going to trace up and down and up and down like this. All right, I'm gonna sort of indicate the direction that my parametric curve is moving in, so the direction that I'm that I'm tracing this out, right? It starts here, and it starts by going up. Well, this is a curve. It's not a function, right? I cannot describe this as a function because it fails the vertical line test. And yet I can describe it as a parametric curve for suitable parametric functions, x and y. And again, maybe I don't explicitly know off the top of my head what those functions x and y are, but let me go ahead and try to graph them. So as before, I'm going to denote two smaller functions here, right? So here's going to be my x of t, describing my x-coordinate as a variable involving t. And let's see what happened to my x-coordinate, right? So my x-coordinate, I started at x equals 0. I steadily increased until I got to whatever this x value was. And then I decreased my x values. So as far as x values go, I'm sort of shooting out a ways, stopping, and then coming back a ways. So I could possibly describe this using a function in which my x value starts at 0, my x value increases in time until a certain point, and then it decreases in time, right? Until at the end of my parametric equation, I'm back at an x value of 0. So again, this is starting at x equals 0, increasing positive x value until we get here, and then decreasing back to 0. That's nicely describing what's happening up here, starting at 0, increasing my x value in time, getting to a point, decreasing my x value in time until it's back to 0. For the y coordinate, right, we've got to do a similar thing. So we want to graph y as a function of t. And what's happening here? Well, my y value, again, at time 0, my y value starts at 0, but then it's going to increase, decrease, and go negative, increase again, decrease again, and then eventually stop at 0. So again, just looking at the y value, it's starting at 0, increasing, decreasing, increasing, decreasing, back to 0. So if we wanted to graph that, we would start at 0, we would increase for a bit, then decrease, then 0, right? And so this point right here corresponds with this point right here. All right, but then we keep going. So now we increase again, we're positive, decrease, and then 0, right? And so that would correspond to our y coordinate. And so what we can see now is we have successfully described this figure 8 using two parametric equations, which are just these two functions, x as a function of t and y as a function of t. And we can do this for any such curve. So that's the idea of a parametric equation. We'll take a look at some explicit examples here in the next video.